So a bit about Vericut and Vericut Optimizer and where this product's come from and what we're going to be showing you and talking to you about this morning. Vericut's really renowned and known for G-code simulation and verification software. But we've also had optimization technology available for quite some time. Now, to have optimization technology, you would always have used to have had the core product portfolio. So you would have always needed to have simulation and verification before you could have optimization. So that was really our product portfolio and how the software really bundles up. So you'd have had to have simulation verification before you could have had our optimization module, which is called Force. Now, as a business, we recognize as our market matures that some of the prospects we talk to about optimization don't really need simulation and verification. They're happy with their CAM simulation, or they may have an alternative product for their verification requirements. So there's not really a need in those cases to buy this part of the product, but you would have had to in the past to have optimization. So what we've done with the Optimizer, Vericut Optimizer, is made it a standalone product. So you don't need the core technology to have optimization. There comes some limitations with this because you don't get all of the good stuff in Vericut, like the collision detection, gouge detection, but nevertheless, you can have optimization as a standalone product, and which is what we're going to talk to you about this morning. So Vericut Optimizer, standalone product. It's just for optimization. It's very, very easy to use. We class this as Vericut optimization for everyone. So it doesn't matter what CAM system you're using. And indeed, if you're not using a CAM system, manually writing code, etc., then you can have Optimizer. It's affordable. It's a low-cost entry point. And really, the mantra here is it's to maximize machining efficiency with Vericut Optimizer. That's essentially what the product's going to do. So what's the problem we're trying to solve? If you talk to any cutting tool manufacturer, they will always talk to you generally about chip thickness and keeping the chip thickness consistent and constant throughout the machining process. So that's really when we're looking at machining strategies and efficiency, keeping the chip thickness constant is by far the most important parameter that we look to do and achieve. So it's our belief that all unoptimized NC programs are not ideal because generally the CAM system or how we program, we concentrate on feed and speed and not chip thickness. So if we look on the right hand side here, generally we program with singular feed rate throughout the NC program. Not all the time. Some CAM systems will adapt a little bit, but generally speaking, we program with singular feed rate. Now, when we do that, that will always result, the net effect is always resulting in a varying chip thickness condition on the tool. Okay. So therefore, NC programs are generally aren't as efficient as they can be. So the solution to this is that Optimizer, Vericut Optimizer, automatically adjusts the chip thickness for each tool operation using Vericut calibrated materials, which we'll talk to you a little bit in a bit, by cut tool engagement. So Optimizer will keep the chip thickness as constant as possible by adjusting feed rates in our NC program, block by block. We will add blocks if necessary, which will result in an ideal cutting condition on the cutting tool. And it will provide a balance between aggressive cutting and prevention of things like excessive forces. So it's a balance of the two. So we're going from an unoptimized process to an optimized process. That's what the software is going to give us. It's going to automatically adjust feed rates in our NC program and keep the chip thickness as constant as possible. It's also going to give us a balance in cutting conditions. So effectively what we do if you look at the toolpath here, as I move my cursor around, each point of engagement I'm highlighting here, generally this would be programmed in a singular feed rate motion. So all we're going to do is break up the blocks and give the NC program different feed rates to account for our different cutting conditions. So coming down here we can see the tool is underperforming. Here we set a limit in the software, so we can increase feed rates in these areas here. So the light green here is generally saying these are areas of productivity, but we can also take out excessive chip thickness. So when we get in too much exertion on the tool or too much force on the tool, we can balance this out by lowering feed rates. So it's a balance of the both and a balancing cutting conditions. Why would we want to do all this? So optimization can reduce your machining time. I've seen more than 30%, but we generally quote between 10 to 13%, depending on the material you're actually machining. So it can give us a faster turnaround on our parts, more productivity. It allows us to avoid tool breakage. Therefore, we can extend tool life because we're balancing chip thickness out with forces. And the other thing to consider here is we can reduce a natural benefit of the software is to reduce our energy consumption and our environmental footprint. So our mantra for optimal cutting is maximize the chip thickness to the tool and the workpiece, keep the chip thickness as constant as possible, and limit our excesses where we need to. I keep talking about chip thickness, and really that's because it's really important. When we underutilize cutting tools, so we're not engaging a cutting tool sufficiently, this can have a negative tool life, and because of the chip formation. So if we underutilize cutting tools, this can really have a negative effect on the tool and the tool life. And this is our opportunity to increase feed rates. And the same, an excessive chip thickness will overload the cutting edge. It will often lead to edge chipping or tool breakage, and the software here will automatically adjust feed rates to limit back feed rates to avoid this. So how does it work? So we're going to get into the software a little bit now. Presentation first, but I will demo some of the software live. But how does this all essentially work? So these are some graphs that we would see in the software typically. And as I spoke about earlier, we generally program in singular feed rate motion. Okay, so we can see this as a feed per minute singular feed rate. So this is an unoptimized NC program. It will always result in a varying chip thickness condition. So all we want to do is reverse this concept. That's all the software is really going to do. So we go from a singular feed rate with a varying chip thickness, and our output, an optimized process, will give us a varying feed rate in the NC program to give us a constant chip thickness. So again, we're just flipping that concept on its head by varying the feed rate motion. So when we look at the two side by side, our input to the software is constant feed and our output is constant chip thickness. One of the first objections we generally have when talking to prospects or customers about Force or about Optimizer is that the perception is that adaptive toolpaths, dynamic type toolpaths are already keeping the chip thickness constant and even. And look, I'm not saying they do a bad job, but they by no means are flat, constant and even. And that applies to every single strategy I've ever looked at, and I've looked at a lot. There's always room for optimization with dynamic type milling strategies. And the example part that we're going to be showing you today indeed uses a dynamic milling roughing strategy or roughing strategies. And there is quite a lot of opportunity still with these type of toolpaths. So again, what would we typically see as the output? Okay, so this will be our input, singular feed rate. We have different points of engagement on the tool as it transitions up this slope. So this would be program and singular feed rate. Our output, we will break up the motion in the NC program, adding blocks if necessary to get the tool or the chip thickness as constant as possible. The software is physics-based. We do have a library of materials which we calculate forces against. Prerequisite is we set a target chip thickness. We have to have a target chip thickness, which is represented by this red dashed line here. But we can also balance these cutting conditions out by limiting forces back. So again, we would reduce feed rates where we have this excessive force, but increase feed rates here where we get more productivity. So it's a balance of the two. But we can also limit by tool deflection, spindle power, and we also optimize air cuts. One of the benefits to all this as well is that before we even optimize is that the graphs produced by the software when we analyze the cutting conditions is that it really gives the NC programmer a visual map of how the tool path is performing from A to Z before we execute the NC code on the machine. So what we can see here is the graphs in the software. And again, I will show you this during a demonstration. But we can click at any point on these graphs, say in this area here. Now that correlates to the NC code. So it will take us to the exact block of NC code where this point is in the graph. And then turn that also includes, it correlates to the graphics. We're not going to get complete simulation. This isn't Vericut, but you can interact with these graphs to see where we are in the process and where that point in machining process would have occurred. And again, with air cutting, we'll optimize air cutting. So what we can see here is that there's no engagement with the workpiece at all. But the blue line here, we can't, if you can make that out where my cursor is, the original NC program feed rate, again, all this non-cutting motion, all of that non-cutting motion was programmed. So therefore, there's an opportunity to increase the air cut feed rate. So we've gone up to 20,000 millimeters a minute in areas where there's no contact with the workpiece. Some of the outputs, we have a compare file. So when we run through our process, we can compare the NC code. If you look at the left-hand side would be our original, and our optimized would be on the right-hand side. We have an optimization savings calculator, so you can calculate maybe the number of parts you're doing or pieces, your hourly rate of the machine tool, our original time versus the optimized time, savings percentage, and you can work out how much money, time you would have saved on that particular component. And also tool use. What we see here is just a very nice visual representation of where we was, our unoptimized process versus our optimized process. We can also produce some nice reports in the software, showing us our tooling, a tooling list perhaps, our original time, optimized time, time difference, etc. And really the process is very, very simple. If you have a CAM system and you have all of these things defined in your CAM system, things like cutting tools, fixture models, program models, stop models, we can embed an interface. The software is standalone, but we can embed an interface inside your CAM system to harvest and utilize all of this data you already have. So all of this data will be sent to Optimizer. So there's very, very little work to do to get you running in the software. Okay, so if you have a CAM system and you've created these things already, there's no need to do that work twice. We can put an interface inside your CAM system to utilize that data that you've already created inside. So just to wrap up on the benefits here, we can typically look to save 15% plus on hard metals, anything up to on aluminium, anything up to 15%. This technology is mature technology. Force has been available in Vericut for a very, very long time. This product has been born out of that technology, so it's not like we're just reinventing things. Force has been on the market for about 10 years. So the technology behind Vericut Optimizer is very mature, very well proven, and very well established. It gives us an opportunity to analyze cutting conditions, remove force spikes, improve your tool life, and protect your spindles. And as well as a natural benefit is we reduce our environmental footprint and energy consumption. So I've got this part here. What you can see is we machined this part recently in conjunction with Seacoat and Grob for our Optimizer product launch. Our overall time saving here was about 25% on this part, and you can see it utilizes a lot of modern machining strategies. You can see in the pocket here. So the overall time saving when we optimize this part was about 25%. And we're going to get into how we actually did that. So the first toolpath I'm going to look at is this one here. It was machined with a 16mm Seacoat 6-flute end mill. The overall time saving, amazingly, was about 33.2%. And we can see it's a dynamic type milling strategy, albeit it was only 2 minutes. It's not a massively long toolpath. But the overall saving was about 33%. So here we can look at the graphs, the before and after. The blue is the before, so this is our unoptimized process. The red is our optimized. We can see the light green areas are all areas of productivity. And what we can see here is how the forces increase here and here. So if I just go back, so as this toolpath was wrapping into these corners, here and here, that's represented in the graph. You can see that very clearly in these areas. Okay, so I'm going to look at the toolpath in the software in a minute. So before I do that, I'm just going to zoom up onto this area. So in the graph, I've zoomed to this area on this next slide. So what we can see is I've got the cursor at this point here. The original feed rate in the NC program was 2004 millimeters a minute. Okay, and we can see as it's wrapping up into those corners, the forces are increasing. When we optimized, again, we're varying the feed rate motion. The chip thickness limit we set was 0.06, and we're decreasing feed rate in that area to 700 to account for these excessive forces on the tool. Again, when we, the other side to this, the flip side is when we look at the productivity, we're not utilizing the tool enough here. So we increase the chip thickness, or increase feed rates to get this chip thickness up. Our original feed rate in this area was 1404.6, and the software increased the feed rate in that particular area to 1930. So we can see the varying feed rate conditions on the tool to get the chip thickness flat and even. And also the air cuts. So with this particular machining strategy, when there was no engagement here, we can see there's no engagement on the tool. The cam system was increasing feed rate motion in that area, but not utilizing that enough. So we can see between this area and this area, there's no engagement. So there's no reason why we can't extend that air cutting motion to give us more efficiency, which is what the software has done in this area here. So I'm just going to play a video of this. It's about 2 minutes, just to give you a side-by-side comparison of the before and after. On the right-hand side is our optimized. On the left-hand side is our original. So that's the optimize done. We can see on the left hand side, that's our original strategy. And that's that one done. So I'm just going to dive into the software and we're going to talk about that particular toolpath. I will also show you how we went about optimizing it, but I'm just going to talk about the graphs for now, and how we come about, or how the software come about optimizing it. So that particular toolpath was this one here. And again, we can see how, if I just look at the original NC program, we can see how the chip thickness really varies throughout the process. Okay, so you wouldn't know that to look at it or listen to it, but these graphs identify how much variation in chip thickness there actually is. So I'm just going to actually add a graph here. We're going to look at the feed per minute. Okay, so here I'm looking at chip thickness, here I'm looking at force, and here I'm looking at the feed per minute. I'm just going to make a zoom up on some of these areas. So if I just zoom to this area and we look at this in a bit more detail, we can see how the software, the original toolpath, it's attempting to increase our feed rates to 50,000 in areas where there's no cutting motion. We can see this chip thickness. You know, there's no motion here, but we're down at feed rate. We can see how the chip thickness isn't as good as flat as it could be. Again, we have excessive forces in this area and in this area. If we wanted to, I'm just going to dock this down a minute. Let's just turn off that feed per minute just to give us a little bit and do a zoom. So again, if I wanted to identify where this area was in our NC program, I can make a click. And in the NC file or in the NC program, that's identified at that motion block. So as soon as I make a click in these graphs, we arrive at the motion block. If we wanted to actually see that, we can review, put the software into review mode. I can click on an area and that will take us to that point in our process. So we can see the tools now arrived graphically at that particular point in our process. We can come backwards, we can go forwards, and this cursor here, this blue cursor, will track up and down the NC program as we come through. So again, this isn't really simulation. It's not going to detect over travels or collisions, but we can look at these graphs and identify problematic areas, let's say, in our machining process, and identify them with the analysis. Just going to come out of review mode. So when we zoom out, again, I'm going to now look at the optimized overlaid with the original. So again, if I do a zoom in, we can see the red area here. That's our optimized program. We can see how that chip thickness has been extended, and I can turn on the field comparison so I can see very clearly as a visual representation that my light green areas are areas of efficiency. And we're balancing those out. If we look at the feed per minute, we can see where our air cut's been extended, and we can see the red line is where we're varying the feed rate motion in the NC program to get this more balanced even chip thickness. Where we have excessive forces in these areas, I'll just do a zoom here, we can see the red areas is where we're bringing feed rates down to account for these force spikes. Okay, so we're capping these down here. We can see that with the red line here. Okay, so I will show you how we got to that point with another strategy, but I just wanted to just make you aware of what we can do with these. So the other thing we could potentially look at is a savings calculator, how much time we've spent or saved on the complete process. If we were making 200 of these parts with an hourly rate of £100, then overall we would save around nearly £2,000 over that process. And again, if we look at one machine over 8 hours, 2 shifts, 220 days a year, we can soon start to see how those savings start mounting up. So yeah, I'm going to come back into the PowerPoint. So that was the first machining strategy we optimized. This is one I'm going to look at now and how we went about actually optimizing this. So this is the first tool path in the process with about a 21% saving. So what we saw in that example just a moment ago was this is the complete process, and we can see all these NC programs is what we actually optimize. It's worth noting we could do subroutines as well if we wanted to. But what I'm going to look at now is how we actually went about and how we actually go about or optimizing the first tool path, just for time more than anything else, how we actually go about optimizing the first strategy in the process. So I've only got the single NC program here. I'm going to first of all come to our tool manager. So again, if you have a CAM system, and what you can see is a representation of all the tooling here, this is how they would come across from your CAM system, as they did in this case. Now, to get going, each tool needs a stop material record, but I'm going to delete this for now because I want to show you how the software creates this stop material record. So I'm going to save that. Now I'm going to ask the software to learn from our existing process. So I'm going to learn from the analyzed results. So I go learn from. I want to set a target directory for our NC program, our optimized NC program. I'm asking the software to append to the existing tool library. I don't want to reset and optimize after it's learned. And I want to create a stop material per tool use. I'm going to optimize our air cut feed rate motion to 50,000. I'm going to limit by chip thickness and force with a learn percentile, and I'll talk about that in a bit more in a minute, with 95%. So we can, depending on what we set here, is how aggressive or where the limits are set to balance out our optimization. So that's really all I have to do to set the software up. Just one dialog, learn from NC program, set a target directory, choose a material. This is a material library, which it's worth talking about. These have all been properly characterized on a Kistler table. In this case, I'm machining titanium. And I'm going to apply that. So I've chosen my material, and I'm going to now start to learn and analyze. So optimization's on, indicated by this yellow light, and I simply hit learn. So I'm not optimizing at the moment. I'm simply asking the software to learn from the analyzed results. So we've processed this G code. I get an option here to reset and optimize, open the tool manager, or just close this window. So I'm going to look at tool manager. So what it's done, the software's done, is created this stock material record on the bottom of this tool structure, and it's populated limits. So it's set the target chip thickness at 0.072, and it's set the force limit at 1919 newtons. And it's done that based on what it's learned from our original toolpath and our analyzed results. I asked it to set the air cut feed rate to 50,000, so that's what it's done. So it's very, very simple to get started and get going with our limits. So when we look at that in our graphs, we go to our subinterval view, and this green line denotes where those limits have been set in our optimization record here. If we weren't happy with that, we can again learn from results, and we can drop that percentile down. Maybe if you just make a visual note of where this green line is, our limit is, if we drop that down to 85%, and if we applied that, then those limits would be set in our force and chip thickness limits. But I'm happy, and indeed all of this project we did was done with 95%. We just let the software take care of where these limits are. Another option you may have is you could put the software into a sorted view. So we're looking at the toolpath here from A to Z. Okay, so that's where we are. But if we sort the view, we're just looking at the averages. So we can see a lot of the toolpath isn't even engaged with material. But then we get this plateau area up here, which may be a good place to set your limit. So you could click on the graph if you wanted to, and you could say save as optimization setting. And if we did that, then the limit would be populated into our chip thickness. Okay. So just to give you an idea of some of the control we have as well, if I go back into my tool manager, I'm just going to dot those graphs for a moment. Now, this started out from a raw piece of billet. I'm asking the software to optimize our air cuts to 50,000, but sometimes we get some discrepancy between billets. If we were machining 50 of these and it would come in from our material supplier, the likelihood is there'd be some discrepancy between those billets. So if they were bigger, for instance, than what was represented in Vericut or Optimizer, and we're optimizing air cut motion to 50,000, or we're machining a forging with some variation, then we could run into some trouble. So just to show you one option, we've got a lot of control within the software. It's very easy to use, but we have a lot of control as well. So just to account for those, I'm just going to give you one example. For those various billet conditions, we could revert to 100% of the program feed rate within 5 mil of the billet. So outside of 5 millimeters of the billet, we're going to optimize to 50,000. Inside that clearance distance, or that tolerance, we're going to revert to 100% of the program feed rate. So I'm going to save that. And that's it really. We can just then hit optimize, start the optimization, and we can see down here we get a very visual view of our optimized process versus our unoptimized. The graphs are being written out here as we're going through this G code. That's hit the M30. It's now finished. Just undock these graphs again, and we can see how we're getting a much better process, limiting back forces where we need to based on the limits we've set, and increasing feed rates in areas where we can. Just to look at the savings calculator, it's around 30%, 4 minutes 06 to 2 minutes 53. So that's how we really go about optimizing processes, and there's not much to it. It's very, very simple to use. This is a video of that particular process we've just gone through. I won't play all of this. I'll play it from there. So we can see this one's finished now, and we've still got quite a long way to go before this one actually finishes. Just to show you some other examples, this is quite a good one where we were face milling. Again, all of this machining strategy was singular feed rate. That's how it was programmed and given to me. I wasn't expecting a great saving, but nevertheless, we got about 21% out of that toolpath. And just to look at the graphs again, areas of inefficiency with air cutting. And as the tool transitions off the workpiece, obviously the engagement drops off, so we can speed up those motions to get a better efficient machining process. Again, here was when they machined the radius at a 20% saving, but it was quite interesting how that toolpath actually looked. I mean, that was the machining strategy. We can see here how as the tool entered into the workpiece, we were getting quite a lot of excessive force spikes, which would be detrimental to tool life. If I just do a zoom in that area there, we can see that in the graphs. If I just play the video, in this area here, we're seeing where those spikes were as it transitioned into the workpiece, which is a nice tool for the programmer to have. But we just let the software take care of that by limiting our feed rates back. And this is where we get the benefits to tool life. Just to talk about the pocket, this was quite an aggressive strategy. And the tool was really struggling for tool life as it was wrapping into these areas. So an 8% saving. But we just took these little limits off here, these spikes, as it was coming into the workpiece, or wrapping into them corners. Again, I won't play all that video. A natural benefit to Optimizer is the environmental footprint, and we could take some data, albeit quite limited, off of the grob that we were machining this part on. So we got some energy consumption data here without Optimizer and with Optimizer. So the first thing, and it's for this machining strategy here, the first one in the process. So it's only for a single toolpath that we did this exercise on, not the complete process. But as an overlaid line graph, which was taken straight off of the Siemens control, the orange really is here. That's our optimized, and we can see with no optimizer or no optimization, the machine naturally used more energy as part of its process. Again, we're a little bit limited on where we could take this data from. It weren't an overall net result of the complete machine, but we were able to just map some axes on the machine, or the axis on the machine, the supply and the feedback. So the feedback is it's almost a bit like a car or a Formula One car, where it returns energy under braking and things like that, and the supply is the overall kilowatt hours. So when we looked at the unoptimized process, for that single strategy and what we could map, it was about 0.3039 kilowatts. When we optimized, it was reduced to 0.32 kilowatts. So that's a reduction. And the feedback where energy is returned, the original was 0.009 kilowatts an hour, and the optimized was 0.013. So it actually is beneficial in both instances. So we worked that out to about 18% saving in energy consumption across that component. And that really wraps up the presentation this morning.